All right, it's 3 o'clock. What do you think? Get going? I got thumbs up in the back. All good? Everybody's here on time? I appreciate it. You guys are great. We do these things a lot here at NVIDIA, and at NVIDIA, we're a little loose on time. And so it's, some stragglers will come in. You guys are all here and prompt. There's people in the front row. This is impressive. I like it. I'm Joe McKinney. I'm your host for today. I have a little bit of content here too as well. We wear lots of hats at NVIDIA. In addition to supporting some Bay Area accounts, I also do the developer relations for our EDA business, and I've had some involvement with semiconductor manufacturing. We'll get to some of those use cases here in a minute. I'm very happy to be joined by Handel. Say hello.
Yeah, my name is Handel Jones. I'm with International Business Strategies. We've been in business about 30 years. We do a lot of the advanced technology analysis consulting, and then we do things like design costs, design starts by geographic region. And then we do have a service, and basically all the major EDA vendors are clients. So we work very closely with them in terms of their technology roadmaps. And then the other area we also do quite a work in is in the AI space, which I'll be talking a bit about today, and then how they will merge in the future.
All right. And then my friend and business partner, Santosh.
Thanks, Joe. My name is Santosh Rao. I want to welcome everybody. I'm here from NetApp today, and want to thank you for taking time out of your busy day to join us. And we have some exciting content. So looking forward to having a education-filled afternoon. But thank you for having us and hosting us here.
Right, it's a great event. Couple logistics, since I am officially the host of this thing, and it's my fault if you guys get in trouble in the building. There are guards kind of outside there. If you need to go to the restroom, they can escort you. The building can be a little confusing. If you're not sure, just keep wandering. Eventually, you'll find out where you're supposed to go. It's shaped like a big circle inside of a triangle. If you didn't get my triangle speech, hang around later, and I'll tell you all about triangles and polygons. We are hosting a happy hour at the end of this. So upstairs, magically, the third floor mezzanine lunch area turns into a bar with beer and wine being served. So you are welcome to join us. I know we all have busy lives and families to get to, but you're certainly welcome to join us for a little bit if your schedule permits. Feel free to ask questions. Mr. Johnson will have a microphone, or just stand up and speak up. And with that, we'll get started. So I'm going to cover a little bit about AI and deep learning in both semiconductor as a whole and some specifics around EDA. But I want to start with some baselines, so I want to make sure we say the same terms. So I'll give you a little bit of NVIDIA overview. Show of hands, are there more hardware engineers at NVIDIA, the GPU company, or more software engineers at NVIDIA? Hardware. Software. You got it. We love the software, so we'll spend some time on that because I'm very excited about that part. And then I'll get you some use cases in semiconductor and EDA. We have about 9,000 people in engineering. We're at 12,000 as an organization. That includes management and overhead, of course. We would say about 2/3, 1/3 is hardware versus software. Is that wrong? Software is the 2/3 number. So yeah, quite a few people. And really, and when I get to it, you'll see why the software is such a big piece for us. It's all about the ecosystem. And that's a great lead in here, because it really is all about the ecosystem. We make the GPU, but the code you interact with at the GPU level is called CUDA. CUDA's been around. We just released CUDA 10. CUDA's been around for about 12, 14 years. Ian Buck, who sits upstairs, is the father of CUDA. And then on top of that, we do AI systems, GPU-based systems. We accelerate algorithms and eventually tie into the applications that drive your business. And why the GPU computing has exploded is really a couple of factors coming together. What we call the end of Moore's law, the single-threaded performance of CPUs, the number of transistors you can pack onto a CPU has diminished over time, and you're at the limits of what physics will allow you to do. Your current generation CPUs do not support the workload increases that you saw in prior generations. The doubling of performance every year no longer happens, and now you're getting a 10% increase if you're lucky. GPUs have not been on that same track. We continue to double or triple performance generation to generation, and I've got the performance stats to talk about that later. So we talk about the platform, the software, and the applications, that green hamburger stack on the prior slide. The software, the hardware platform, is based on the GPU. We have a number of ways that GPU is delivered. NVIDIA GPUs are available today from every cloud provider on the planet, from every OEM, every ODM. You can get them in your laptops, in your desktops. You can get them in robots. You can get them in drones. GPUs are a ubiquitous computing accelerator available everywhere you need it. But that isn't enough. Lots of people can make great hardware. Some of our competitors make some amazing hardware, but they don't have the software ecosystem. So if it starts with CU, it probably runs CUDA, fairly low level, libraries and SDKs for SPICE. Anybody heard of SPICE? For sparse math, for matrix solver, for random, for FFT, for Fourier transforms. We'll get to some litho and math stuff in a second. Deep stream is some video analytics. We do inference engines for inferencing both at the edge in your remote device, as well as in your data center. If none of that makes any sense, go up a level, and you can use GPU natively in a bunch of off-the-shelf applications. Every AI deep learning framework is accelerated with GPUs. There are more than 500 applications that natively have GPU-enabled code inside of them. It's quite likely an application you run in your business today you're not aware of is possible to accelerate with a GPU. And what that enables is the use cases on top. When we talk to our customers about the problems they're trying to solve, this conversation goes in reverse. I'm trying to figure out how to understand my customer better. How do I do that? I'm using AI applications or high-performance compute or machine learning. I'm running these libraries, these algorithms, and I'm doing it at my compute center. So this is how we look at our customer and how we approach the business. So this is, I want to give it some foundation of both the hardware and the software stack. And I can't go on without showing pictures of the kids. So this is the NVIDIA Volta V100. This is the highest end universal GPU. Today this runs every AI application, every HPC workload we have. Double precision, single precision, half precision, int4. It has tensor cores, which is a specific ASIC built for matrix multiplication. Quite a bit of processing power crammed into this little card. And again, available everywhere on the planet. We also recognize not everybody has 300 watts to give to their compute, or they want compute at the edge, or they want an inference-specific GPU, and that's what the T4 is. This is relatively recently announced, dedicated to inference, and some of the specs here. Also has the Tensor Core ASICs as well. And I see some notes being taken. These slides will be made available, so you're welcome to take notes if you like, though. Very proud of the performance, very proud of the ability to accelerate all the workloads that people run on GPUs. Now, it's not enough to build the GPU. We also recognize that sometimes we wanted the system to get in somebody's hands and have them have the fastest experience possible. So we built AI supercomputers. This is a DGX workstation, goes right under your desk, plugs right into the wall. You can buy them today. This is the DGX server, DGX1. It's 8 GPUs connected together via our high-speed interconnect called NVLink. And on the right-hand side is the recently announced, now shipping DGX2. This is 16 GPUs connected at full bandwidth. Each GPU can talk at full bandwidth to every other GPU in the system. And so from a compute standpoint, this looks like one big GPU. And so our designers are just chomping at the bit to get these because this thing is an amazing 2 petaflop compute engine. Any data center people in the room? Facilities, data center ops? Good. They hate that. It's 10 kilowatts and 10U. They're going to cry. But it's amazing from a compute density standpoint. It's 2 petaflops. Anybody work on supercomputing in college? Do you have a 2 petaflop machine that take up this size of a room? So the density is amazing, the performance increase is amazing, the ability to do this, and not just the hardware, but the entire software stack. Through NVIDIA GPU Cloud, we provide all the AI frameworks, 41 different containers, proven, known, good working, supported by NVIDIA, distributed monthly for free. So your AI workloads can get started today using NVIDIA GPU Cloud. Now, when you build these systems, it's great that you have the GPU. What server do you put it in? Well, talk to your favorite OEMs. You build the DGX and you say, I want to do all this AI number crunching, but I got to get the data from somewhere, and I got to put the data somewhere when I'm done with it. And that's not our area of expertise. For that, we count on our partners in the ecosystem. And NetApp has been one of our best, most engaged flagship partners to help create an AI stack. So this is a reference architecture built between NetApp and NVIDIA, combining their high-performance storage with our high-performance compute and giving you the best experience out of the box with a known, good, working reference architecture. You can start today and say, I'm ready to go and run that using NVIDIA GPU Cloud, DGX, and the NetApp flash arrays, and have a working, known, good system for your AI workloads. Let's talk more about software. I'm going to go just always left to right here. Just take your applications today. Many of them are GPU accelerated. If you're not sure, we have a list, and I can tell you which ones are GPU accelerated. If you want a little more engagement, a little more control, you've got AI data scientists who want to dabble in the frameworks. You're not sure if you should use PyTorch or MXNet. We can help. We work with all the frameworks. We give code back to the frameworks. NVIDIA neural network software is embedded in every AI framework. You want to operate at a lower level, write code directly. You're doing linear algebra. You're doing sparse math. Call a library. Not sure if your code can be accelerated? Homegrown application? OpenACC is a free set of compiler hints and directives that you can recompile with, and if your code can be GPU accelerated, it will put it over there on the GPU. You don't have to do anything other than recompile. And then if you really want to get down to the lowest level, have the most involved experience, you can code in Fortran. Or I'm sorry, geez. Yes, you can code in Fortran. There is cuFortran if you'd like to do that. C++ CUDA. CUDA is our programming language, taught at 1,000 universities. Every high-performance compute shop on the planet takes courses in CUDA. We offer courses in CUDA. And so what that drives is this entire ecosystem that drives the function of AI and deep learning. NLP, customer analytics, image recognition, all the things you're going to see applied to the use cases in Semiconductor here in just a moment. Now, deep learning is one segment of the AI umbrella. The next segment is machine learning. And for a while there, we really didn't have anything in this space. We just recently announced something called Rapids. This is an open source effort from NVIDIA providing machine learning libraries. So this is the AI ecosystem. Here we have a number of the most common algorithms run in machine learning. These traditionally have not been GPU accelerated. Today they are with Rapids. So we are working with XGBoost. We are working with k-nearest neighbors, working on clustering, linear regressions, SVD. Anybody do PCA here? I know your engineers are. These are workloads we can now accelerate that we couldn't a year ago. So this space keeps moving faster and faster and faster. We are looking for more workloads to put on GPUs, and the numbers here are significant, as our friends at Walmart say. So it is changing the way they do demand forecasting. Now that's a retail application, not an EDA, but it's still XGBoost. It's still manufacturing planning. A recommendation engine at a large media company said we made it too fast. So the same acceleration we've brought to HPC, the same acceleration we've brought to deep learning, we're bringing that to machine learning now with Rapids. It's available today, free, open source. All right, let's talk about some examples in your ecosystem. We look at semiconductor and EDA under the industrial manufacturing umbrella. That's how NVIDIA segments the world. So we'll talk a little about the manufacturing space, some examples from our friends at KLA, and some examples in NVIDIA as well, in electronics manufacturing. Every year in San Jose and around the world, we host a GPU technology conference, of which NetApp is one of our sponsors. This year there were 23 sessions on industrial manufacturing, predictive maintenance, field analytics, field repair, time to repair estimates, digital twin product lifecycle, industrial inspection, semiconductor inspection. We also had one on masking as well. So GTC is where the people that are doing these applications will come talk about their work and share their science. It's a forum March 28th through the 30th this year, 2019, is the next one coming up. There's also one in China, Japan. We just had one in Israel. So we do them around the world as well. Get into a couple of applications here. Anybody familiar with Foxconn? I don't have to explain what a contract manufacturer is. Excellent. So they're using AI to improve the manufacturing process. The common threads here that you'll see through a lot of these is, can I increase yield? What does a 1% increase in yield mean to you? I know what it means to NVIDIA. When we talk about this internally, this is critically important to us in our business. So wherever we can help our partners improve yields, that helps us be more profitable. So this is near and dear to our hearts. So we work directly with Foxconn to help improve some escape parameters that they had for one of their manufacturing lines. So this is applied in the factory. This is a use case from within NVIDIA. Head and pillow defects. Anybody familiar with those? This is a VGA connection solder joint problem. Yep. So this is really hard to find. This gray blob is good. That gray blob is bad. Really hard to look at. Very time consuming. Scanning electron microscopes involved in the process. We've discovered we can use deep learning We can use generative adversarial networks to create more failed images and increase our prediction rate by a significant percentage. This reduces the product defects. This helps us find where in the line we are having these problems before the GPU goes out the door. This is we're using AI to improve our own products. We've got a much further in-depth demo on this, but we are able to find the difference between these two things without taking the time to scan every joint with a scanning electron microscope. Our friends at Seagate do something similar for platters. So the next set of disk drives you get in your arrays, well, I'm dating myself here. Platters, who uses platters anymore? But the image analytics, the defect analytics is a very similar convolutional neural networks used. I find defects on my platter, I find defects on my wafer, and I use AI to analyze this. So Seagate is using this in production today. Everybody know what that is? It's a wafer. So similar, I'm looking for die inspection on the wafer. So these are some of the research projects we get involved in, is working with these manufacturers to understand how we can improve the yield of their products, where we can find defects in their products, and our ask is that we publish. And so you'll see a lot of this is all publicly referenceable information because these are people that are moving a state-of-the-art forward. Litho masking, our friends over at D2S. This is a very large function FFT to be able to do the curvilinear designs. So if you're interested in litho masking, these guys are using GPUs, and they have said, Aki has said a number of times that his company would not exist if it wasn't for GPUs. Hotspot detection. We also have an example later on coming up about self-heat. So finding the hotspots on the semiconductor itself, improving design and layout, place and route. These are all areas that we are working with ASML on. And again, mostly convolutional neural networks, as you can tell. That's fairly state-of-the-art, fairly standard. Anything with image. If I can look at it, a computer can look at it, and a computer can do it better and with more precision. I mentioned GANs, generative adversarial networks. This is basically fake data, not fake news, fake data. I take examples of bad data where I don't have enough examples of bad data, and I use AI to generate more examples that look like bad data, and as such I can improve my training data set such that my engine can find more faults than previously before. I improve the ratio, improve the probabilities. Chip self-heat, this is a problem we worry about. GPUs run a little hot. So we are looking for exactly how to avoid self-heat and then how to dissipate that heat, and we're using AI and deep learning to solve that problem. This is actually our own research. So we presented DAC. So if you were at DAC, you would have seen this. More self-heat stuff. I like this one a lot because this is AI. This is deep learning versus machine learning. Machine learning on the left, deep learning on the right. This is just a standard regression, and this is the same regression run through a neural network. We do some acceleration at HSpice. That's using CoolSolver. We can talk about that later. And decreasing the error rates are pretty significant. So I talked earlier about yield. If I go from an 11% error rate to a 5% error rate, what does that mean for our products? We already bought the wafer. So we're very excited about being able to improve all of our products by moving from machine learning to deep learning. Our friends in inspection have a very big challenge. Today at a 10 nanometer process, that is roughly the size of a DNA strand, maybe twice the size of a DNA strand that you have to find very, very quickly. Very big challenge, and that gray blob is good. A different gray blob is bad. So using neural networks, using image recognition, you're able to increase the ability to find optical defects in your wafers. A little more on how they do this. Jing presented this at GTC last year. It was the very last session on the very last day. We had broken down the show floor was closed. His room was absolutely packed. This is a topic everybody wants to talk about. So this is a very interesting use case, and we've really enjoyed the collaboration with KLA on that. We'll keep going. So more about how that works. See, gray blobs got better. And then our friends at Synopsys are also doing this. So this is not just on the manufacturing side. This is also in the software side. Traditionally, EDA software has been single-threaded and not very parallelizable. And I think the Moore's Law impact is impacting them and their business. and their customers are demanding more acceleration. So we're working with Synopsys. The guys that do TCAD allowed us to publish this. I don't think it calls it out. Oh, maybe it does. This is one GPU. This is one V100. That one earlier, the picture of the kids, the little flat one. That's one GPU in a system. That is 80 times faster than a CPU. This is so fast you don't believe it. This is so fast that you think something went wrong. Somebody truncated half the data. This is so fast that you're not sure what you're supposed to do with this. Because something that used to take a week now takes a minute. This is 80 times faster. That's one GPU. Now we'll get into the sales side of my job. A little TCO math there. 80x performance is pretty good. GPUs are expensive, but if I can make it go 80 times faster, I can make your simulations go 15 times faster. I'll get to that in a second. Very significant speed ups to your business on a critical design workload. Same thing in simulation. So we see a similar impact, similar acceleration. And notice the multipliers we talk about. Yes, sir?
I'm a TCAD user.
Awesome.
I'm wondering, is this commercially available?
Commercially available from Synopsys. I can't speak to the others. Yes, I would not be able to present it if it wasn't. I can't share NDA. It's your NDA, not mine.
So which tool is this?
I don't know the name of it. It starts with an S. I can tell you afterwards.
Centaurus?
Yes. No. No, it starts with an S. I have it because I have all the full deck on this. I can show it to you later. Find me at the happy hour. And not to be left out, many of our other friends in the space, if you run Cadence Virtuoso, that workload can be accelerated. We find examples of people running Virtuoso on designer workstations using NVIDIA Grid, which is a VDI workload. We can accelerate your virtual workstation and delivering that workstation to the end user. The speed up in Virtuoso is pretty significant. Not a lot of people have heard of Ansys. They acquired Red Hawk a few years ago. Ansys is mostly, you know the Ansys guy too? Yes, absolutely. Red Hawk is GPU accelerated. And if I kind of think about it a little differently, building a building and building a semiconductor or building a chip, maybe 3D NAND, are fairly similar if you look in structure. Ansys has a lot of experience in the CAD CAE space, and their acquisition of Red Hawk moved them into circuit simulation and EDA. And so we're very excited to work with Ansys. They've been a longtime partner of ours on the CAD side, and now they're branching out into chip design. Very excited about SPICE. cuSolver in CUDA 10 includes some SPICE acceleration. There are some developer interactions we need to have if you want to try that, so we need to talk about that. That's a non-trivial thing to go do. Desensing for RF is commercially available from CST Studio. And then, of course, some of the verification workloads. So we see workloads all over the place, and these are the ones we do internally. So before this, I went to the VLSI team, I went to our DSP team and said, what are we doing? And they gave me these. And these are the ones we're comfortable talking about that we'll be presenting at GTC in March. There are quite a few more in research that we are still engaging on. So we are very excited about this space. I think it's very exciting to me that EDA will eventually be a parallelized workload, and when that happens, we will be ready for it. So that's all I have to share today. Hopefully you've gotten a little bit about kind of where we are. I'm happy to hang around for questions. I'll be here because I'm your host, and I'll be upstairs tonight as well. I'm going to turn the floor over to Handel, but any questions in the meantime? Super. All right, sir. Yes. Excuse us while we...
The mic is not on, sorry. Thank you.
So I'll go off script a little bit for a couple of minutes. What do we see in the semiconductor and electronics industry? Right now, it looks like we're getting into a slowdown. Basically, we're seeing some softening in demand. And so if you look at the guidance from some of the semiconductor companies, basically revenue is flattening, revenue is potentially down. We think, though, this is a short-term phenomenon. We're actually raising our forecast for the semiconductor electronics industry, and a key factor for that is because of AI. So where do we see AI coming in? Obviously, autonomous driving is one area. We start seeing IoT starting to come in because of NB-IoT. We also see the big data in terms of data centers. And then we also see the impact of 5G. The other side of the coin, though, is that we also do design costs. And we see design costs increasing quite rapidly as we go down in feature dimensions. At 5 nanometers, an 18 square millimeter chip, which will have about 10 billion transistors, will cost about $500 million. Hardware will be about 200, software will be about 300. And what we are seeing on a global basis is a shortage of design engineers. So from an EDA point of view, we do track the activities on Upsys, Cadence, Ansys, Mentor. We see improvements in capabilities, but we're basically running into a wall in terms of a small number of designs being implemented. So if you look at 5 nanometers or 7 nanometers, you've got Apple, you have HiSilicon, you have NVIDIA, you have Qualcomm, AMD, potentially MediaTek, and then basically some small companies maybe doing some AI chips, but that's what's going on, basically a fairly small number of companies. If you look at 28, maybe we have, in fact, I'll give you the number. We have this year, design starts at 7 nanometers at 100. If we look at 28, we have about 2,000. So we have basically this issue now in terms of going to smaller feature dimensions. What you have is increased difficulties or increased costs in terms of implementing designs. So what solution do we have? Our solution is to provide or to develop what we call mega design capabilities. So we have the foundry business model. We have TSMC, basically, 33 billion, 34 billion, basically providing a whole range of process technologies. We think the same thing has to happen in design. You can't basically, when you go to 3 nanometers, basically we think you have to have a design factory. And of course you can input your specifications, you can maybe decide what IP and so on. But there's no reason for place and route to have design engineers. When we look at design costs, 75% of design costs are engineers. So basically we think that with AI in the future, what we talked about was shown supercomputer capabilities, we think that part of the design process will be automated. Maybe it's 5 years, maybe it's 10 years, but basically that's the way we think you can stimulate the industry and basically take advantage of AI. So in terms of IBS, we've been in business 30 years. Actually, I spent a lot of time in China. I go to China probably every 6 weeks, and we've actually done 3 books on China. The latest one came out a week ago on impact of artificial intelligence on China in 25 to 2030. And it's, basically, we'll see how well it sells. So the phase we're going into today is data. Obviously, data generation is exploding. And we have data processing, we have data analytics, we have data storage. But the other thing that we're getting into, of course, right now is data is becoming an asset. So how do you get value from data as an asset? So, of course, Google is doing this in terms of some of the stuff they're doing it. Amazon is doing it indirectly in terms of how they deliver goods. But the concept of data as an asset is a fairly new concept. And of course, you need high level of security. You need basic encryption capabilities. And of course, as I mentioned, you need much higher levels of processing power. And of course, you need much larger storage. In terms of generation of data, the smartphone is a huge generator of data. And of course, it's the camera that's the biggest generator of data on smartphones. The automobile will be a huge generator of data as autonomous driving comes in. Also now we're going to see in the next 3 or 4 years, IoT becoming significant. To date, IoT has not gained significant traction because there has not been a viable way to monetize data. And also there has not been an efficient way of transmitting data from the sensors to the cloud. So LPWA, well, basically specifically within that NB-IoT, in our opinion, becomes a way to transmit data very cost effectively into the cloud. And then, of course, once it's in the cloud, then you can start processing and generating value. In terms of NB-IoT, the leader is China. And the plan in China right now is of 80% of the population covered by Q1 of next year. And of course, behind the NB-IoT will be 5G. And in China, 5G will come in fairly significant volume in 2020 and 21. And part of a key driver for the initial adoption of 5G in China is not just a smartphone, but autonomous driving. And in the US, unfortunately, we're doing fixed 5G as opposed to mobile 5G. So we're not going to have the same kind of momentum in 5G as we see in China. In fact, China is planning to have 1 billion 5G users in 2025 to 2028. So we do see different types of data, dynamic data, static data, and so on. And of course, there are different ways of monetizing data. As I mentioned, the most important capability in terms of AI is processors. And I'll show you a bit more about processors in the next few minutes. Of course, GPU is a key capability in this space, but we see new architectures coming in. A TPU architecture is significant in our opinion. Commercializing it, of course, is going to be a challenge. But the key issue in terms of the TPU is the closeness between memory and the processor. So memory, one of the biggest limitations today in terms of performance and cost is the relationship between the processor and memory. And of course, you can do HBM2, which is expensive. You can do wide memory. But that's an area that new architectures will have to solve. And we know a number of activities in that area, including in this company, which have not been announced, which we can't talk about, but in terms of how to access memory more effectively and how to have more efficient interface between memory and the processor. And then what we do see is that AI is actually at a fairly early stage of adoption. And the analogy that we have for you is that when oil first replaced blubber in terms of lamps, nobody thought about what we would have today in terms of, aircraft going at multiple speeds of sound. Of course, when we've traveled commercially, they've slowed them down to reduce fuel. But basically, in terms of how we can build tall buildings, etc. So what we've had in that space is the extension of muscle power. What AI will do is will extend brain power. And I'll talk a bit more about that in the next few minutes. So you're going to have the generation of a wide range of new industries. And of course, how companies operate businesses, how people do different tasks is going to change dramatically. The smartphone you have today, in the next 5 to 10 years, will be able to do 98% of what you do today more effectively than you can do it. So how the brain gets used, how society operates, how companies operate in future will change dramatically. So again, what we had with the oil, 150 years, what we're going to have with AI is 15 years. So again, we're going to go through some major changes, and it's really exciting. And it's going to create, in our opinion, high growth for the electronics industry, high growth for the semiconductor industry, and of course part of that also will involve more storage, more capabilities, but a whole range of new opportunities. So what are we going to see in terms of industry? AI will basically obsolete, or robots will effectively obsolete 500 million to 1 billion workers in factories. So when we go into, if you go to a wafer fab today at TSMC, almost no people. Basically, defect density has come down, cycle time has come down. Before TSMC was 1.4, 1.6 days per reticle. Now they're down about 0.8 days per reticle. Go to the new factory of Samsung in Pyeongtaek, almost no people. So a lot of the tasks in terms of what's being done by people today will become obsoleted. And of course, who is driving that? Foxconn, Honai Foxconn. Basically developing robots. And again, whether this is going to be in 2030 or 2035, there's some issues there, but it's going to happen. We're going to obsolete a lot of the jobs in service industries. When you go to check into a hotel, basically you're going to have a 3D facial recognition, and Marriott is already doing this. They'll recognize you, go to the room. What we're seeing right now in terms of shopping, you go in, you basically do the 3D facial recognition, you can buy things, and no need for people. So a lot of the service industries will be obsoleted. Now, of course, the issue is when we had oil basically replacing fish, people catch fishermen and so on. And if you also look at the agriculture industry, we found new jobs. But again, we have to do the same thing here. Basically, we have to find new jobs, new careers. And of course, people in the electronics industry, this is actually a good industry to be in. But it's going to involve significant changes. We're doing a lot of work in the autonomous driving. What we're going to see in the first phase is basically the adoption or the integration of the processors. Of course, the GPUs of NVIDIA are becoming increasingly used because customers want lower power, lower cost, and so on. And you've also got Intel with Mobileye. So initially, it's going to be for the reduction of accidents. Level 4, level 5 is going to take a number of years to happen in the US. But we think in China it's going to happen faster, though. And of course, there to reduce traffic congestion. And also, it ties in there with the electrification. We do see electric vehicles. Last year, it was about 1 million electric vehicles. In 2025, 2027, you're going to have 40 to 50 million. But as you basically go to autonomous driving, the number of cars needed will go down. But the other side of the coin, though, is the miles driven will increase. And of course, when you have Uber in San Francisco, actually there's more congestion because they have to come and get you as well as taking you. So part of the adoption of autonomous driving will be also the setting up of autonomous transportation and then smart cities. So that's an area, those are areas that we're starting to see develop. But again, as I mentioned, the rate of commitment in China is significantly higher than in the US. And Baidu is leading it. And fairly recently, Huawei demonstrated with Audi level 4, basically initial level 4. Of course, you're not going to have practical use of it for a while. But again, major commitment to improve traffic flow. The other problem China has also is they produce 30 million cars and basically saturation. So this year, volume is down 15-20%. So to continue with the factories running at the rate they're running right now, they have to basically find new applications and also export. The other issue that we look at extensively are smartphones. You know, what has been achieved by the smartphone vendors in terms of, Apple, Samsung, right now HiSilicon is amazing. And if you look at the processor functionality, the processor that you have in the smartphones is pretty amazing. But performance will be increased by approximately 100x over the next 10 years. And the big next step that we see right now is augmented reality. And augmented reality basically involves time of flight, measurement distance, and so on. But at the same time, though, we're seeing the embedding of neural network cores. And of course, that will provide significant additional functionality. So what you're going to see, in our opinion, as I mentioned earlier, is the processing power, the analytics power of your smartphone will be significantly superior to what you can do for most of the tasks you do today. So it's going to be a major asset if it's used properly. If it's used improperly, of course, it's a detriment. The other area that we're seeing that AI will be big will be preventative medicine. The Apple Watch 4 is actually a very nice device in terms of measuring arrhythmia. But the big application is that of the measuring blood sugar level, and without drawing blood. And that technology is being worked on in a number of companies. And I think in the next 2 or 3 years, I think you'll see practical use of that. Maybe not on a wearable device, but basically in terms of a device that you can carry around with you. But of course, what you can then do with these wearable devices is basically determine diet. And of course, the whole thing, as I mentioned, is preventative medicine, not curing of medicine. VR is going to come in. The biggest limitation today is display capabilities. And of course, the first set of AR capabilities have not been particularly successful. But we think in the next 5-10 years, you're going to have significant enhancements in displays. Of course, you need much higher levels of processing power. I think the leader of NVIDIA has said that the GPU, and correct me if I'm wrong, performance will go up 1,000x by 2025. Okay, so basically we're going to see this huge improvement in performance. And then when you have VR, basically you don't have to be here. Basically we can have this meeting without you being here. So again, that's going to change working patterns significantly. But all of this will require high performance semiconductors, lower power semiconductors, and also a much broadening base of power semiconductors. You know, we just did an analysis of image sensors. Image sensors, basically, there's going to be 19.6 billion image sensors in 2027. And we said, okay, today we have 4 billion. How much wafer capacity do you need? And I think we came up with about 200,000, 250,000. So we looked at Sony, we looked at Samsung, and so on. Then if you look at the 19.5 billion, how much wafer capacity you need? Over 1 billion a month. Over 1 million wafers a month. And it's in 28. So maybe you can move basically, 45 down to 28, but you need a lot more capacity and a lot more. And then of course, when you have the image sensors, you then have the ISPs. And of course, ISP is attached to the image sensor. And of course, you have a separate ISP, which is now part of the smartphone, the application for a smartphone. So again, that's one example of where you're going to have significant expansion of products, capabilities, applications. And of course, we have to improve design productivity because we don't have enough design engineers. We actually did a recent analysis of how many people do you need to do a chip at 5 nanometers. So this is IP qualification, the architecture, verification, emulation, place and route, validation, then the supply chain. And it's 2,500 engineers, 2,500. So we know how many engineers basically we have in this company, we know how many are in Cupertino company and so on, but it takes a lot of engineers. So we have to reduce or make them more efficient to do more designs. So as I said, oil basically impact in 150 years. AI is going to be in 15 years. So basically we're in a very fast changing environment. So as I mentioned, throughput of processors is going to have to improve significantly. So we have basically this chart over here. So the bottom, we do have processors going up effectively 1,000x by 2030. So NVIDIA is saying by 2025. Then we also have the algorithms also improving significantly. I think CUDA, as mentioned earlier, is an incredible capability in terms of developing new software and so on. But the best algorithms today are DeepMind in the UK. But the algorithm performance will go up, in our opinion, by 1,000x. The other thing that also happens is as you generate more data, you basically, data itself generates more data. So the amount of data that you generate also will go up 1,000x. So when you accumulate those, basically the amount of data that you analyze, the processing capability, and the amount of information that you can obtain goes up almost exponentially. So this is the world that we're getting into right now. And of course, we are going to 5 nanometers. We think it'll be delayed because of issues with EUV. 7 is ramping very fast. We actually did a cost per billion transistor analysis. Actually, we based it on the Apple chips. So we looked at 16, we looked at 10, and we looked at 7. And billion transistors for the 7 nanometer costs about $3. So the Apple chip, the whatever it is, A12, costs about $18. And that's got almost 7 billion transistors in it. Now, of course, NVIDIA have a higher number of transistors, and of course, they charge a lot more than that. But basically, that's the level we're at. The chip costs $18 for 7 billion transistors. But of course, after 5, we can potentially go to 3. Gate all around looks like a challenge. So I think we're going to plateau. So again, the throughput enhancement will come mainly from new architectures. And as I said, new architectures involves the processor, many cores, and then the access to memory. And of course, how we access memory, in our opinion, will involve some significant compilation capabilities, which again will be AI based. So the capabilities in processors, the leadership today is clearly in the US. So we have NVIDIA, we have Intel, we have the TPU, we also have some startup companies, but we also recently did analysis of the AI processors in China. And we found about 10 that actually look fairly reasonable. So you go back 3 or 4 years ago, there was basically nothing. So Cambricon is in there, HiSilicon is in there, HiSilicon is working with Cambricon. But again, we do see some significant investments and significant breakthroughs in terms of some of the AI processors coming out of China. HiSilicon just announced their Ascend 910 is 350 TOPS, 350. And it's in TSMC 7 or 7 plus. So again, we basically, it's a global, or maybe global, it maybe isn't, it's really China and the US in terms of the development of the concepts. And again, I think it's good to have competition, but I think it has to be done cooperatively. So this is an example for you in terms of what we're seeing in autonomous driving. This is the market for the ADAS processors. Today, basically, it's 2 companies, NVIDIA and Mobileye, and we do see new companies coming in. Level 5 capabilities will be installed because of the reduction in terms of accidents, but as I said, in terms of adoption in the US, probably 10 years, maybe longer. But again, in China, it's going to come in faster. But you can see basically how fast this is moving. Now, in addition to the ADAS, you also have the camera modules. And the camera modules, you're going to have 16, 18, 20 camera modules per car. I think the Teslas already have 16 or 12 or 16. You also have radar, potentially LiDAR. And of course, the integration of those inputs to give you basically the ability to have a self-driving car involves very high processing power. So you can have multiple levels of cloud, and of course you can't take that into the enterprise cloud because of delays. So you can have local cloud, so within the car you're going to have a cloud, you're going to have a cloud above the car. The car companies will want to know where the car is, they want to have a cloud. If you have Uber and so on, they're going to have a cloud. So again, you have these multiple level clouds, and of course connectivity, the option of course is 5G. 5G gives you fairly low latency, but again, because of the amount of data, there's not going to be enough bandwidth available from the carriers. You know, I think one of the problems we have in California today in terms of even using 4G is the carriers are basically threatening demand. If you look at the modems from Qualcomm, even from Intel, basically we're talking about 300, 400, maybe 500 megabits per second. If you get 20, 30 megabits per second, you're lucky. And of course, part of it is because they don't want to make the capex. The other part is they can't install the base stations because people object to having base stations in their backyards. But again, not only will you have processors here, but you have a whole ecosystem that will now build around autonomous driving. As I said, the image sensors, the radar, and then the data management and the data analysis, data analytics. So again, this in itself is going to become a huge industry. And of course, you can't do it by adding people. You have to go to the next level of processing capabilities with AI. And so we do see some significant activities right now among companies. Again, we can't tell everything we know in terms of using the AI capabilities to do the analytics. And of course, a number of them are in the Bay Area. And so in addition to the autonomous driving, what we do expect to see again is autonomous transportation. And of course, you're going to then have to have what we call smart cities. Alibaba is installing right now 150,000 sensors in Wuxi in terms of trying to improve traffic flow. And of course, that's very limited. You're going to have potentially 1 million image sensors. This is one city in terms of monitoring traffic flow, in terms of how you do the traffic lights, etc. And of course, eventually you have to get pedestrians off where cars are so that there's no basically potential reduction in terms of life. So this is what we show in terms of 5G, basically potentially going to initially 10 gigabits per second as peak download, potentially longer term 100 gigabits per second. That could involve millimeter wave, but millimeter wave and motion are very difficult. Millimeter wave doesn't go through buildings very effectively. So basically most of the market will be the under 6 gigahertz. And in terms of the leadership, modem leadership today is Qualcomm. HiSilicon has a competitive modem. Intel just announced their modem, Samsung has a modem, MediaTek, and that's probably it. And of course, modems will not only be used in smartphones, but also, as I said, in automobiles. So again, when you have this kind of bandwidth, this creates a wide range of new industries. Agriculture is another area where we do see AI coming in. Medicine will be huge. And of course, you can do remote diagnostics, you can do a whole range of things in terms of use of AI for medicine. But again, all of this require basically silicon. So when we look at the smartphone market, when we look at 5G, you can see China is actually significantly bigger than the US. And again, the reason is they've made it a national commitment to have mobile 5G. In the US, we tend to be more concerned with short-term profits, AT&T buying companies to do content as opposed to focusing on bandwidth. So again, I said here we're doing the fixed, which is not the right way to go in our opinion. The other issue in that space, though, is that when you look at base stations, Huawei is 1 year ahead of Ericsson in technology, and Ericsson's 1 year ahead of Nokia. But of course, we're not going to be allowed to have Huawei base stations in the US. We're going to have them in many parts of Europe also. So again, so in our opinion, 5G will expand, obviously, the capabilities of smartphones. It basically will allow support of autonomous driving and also will support IoT. And it won't be the distributed, 1 million sensors or in a city. It'll be really the high bandwidth applications, such as the medical applications, factory automation. We do see the concept of digital twin coming in terms of manufacturing. And we're also tracking now blockchain. Blockchain in manufacturing is going to be a huge, huge industry. We're tracking semiconductor activities in blockchain where you basically have to manage the supply of raw wafers. You basically have to manage the processing in the fab. You have to manage each piece of equipment. Then you have to basically look at the chip design. You look at testability. You have to trace it to the design to how you do design. And then when it goes in the system. So these things are starting to emerge. And of course, the issue is you have multiple databases. Each database is proprietary to a company, so there has to be encryption. So if you're growing silicon wafers or doing silicon wafers, you don't want TSMC to know how much capacity you have, because you really have to be able to basically maybe provide, tell them, oh, we have shortages, you have to raise the price. And in the same way, TSMC might not want equipment vendor to know exactly what's going on in terms of their fab, etc. So the database will be separate, but encryption capabilities are required, and they're being developed. And again, you need more processing power, you need more storage, and again, you need more semiconductors, and you need more efficient design capabilities. So again, as I mentioned, we do have 1.6 billion smartphones being manufactured a year. If you have a content of $10 on a smartphone, your market potential is 16 billion. So that's where we do see a lot of activities right now in terms of enhancements in capabilities of smartphones. So if you look at the wafer volumes going forward, or even at 7 nanometers, probably 80% will be smartphones. So TSMC talks about HPC and so on, but in reality, 80% of the wafer volumes are smartphones. And in smartphones today, that's actually driving 7. So Apple basically, if you look at their chip size, you can figure out how many wafers they need. So they need about 40,000 wafers a month. And then high silicon needs X number, maybe 25. Qualcomm will take, and then you come up to the 85. And then you see basically the graphics guys, including NVIDIA, being a little bit behind. But of course, they need the high performance. They need the basically high yields. And frankly, it's going to be the high performance chips that actually drives EUV because of the reduction in interconnect delays. So I think we've covered most of the points on this phase here. So again, when we look at the area we track fairly carefully is data centers. So this shows right now the CapEx in data centers. And you can see that most of the CapEx right now, we're looking at 2018, is Alphabet, basically Microsoft, Amazon, and Facebook. And you see the Chinese are fairly small. But in the next 3 or 4 years, Alibaba is saying they'll have more capacity than Amazon. So we expect to see this CapEx accelerating significantly. And then if you look at the semiconductor consumption in CapEx or data centers, you see process at the top. In 2027, we think it'll be about a $57-60 billion market. Intel today is about 20 billion. NVIDIA, we know what the NVIDIA numbers are. So I think basically the growth in terms of processor revenues will be significant. And we think the x86 architecture needs to be refreshed significantly. And so again, we see new architecture come in, also the core processors. Also, you look at the DRAM. DRAM prices are high because of the shortages. And why do we have shortages? Because the companies making DRAMs figure that if there are shortages, they get high prices. So 3 companies have 96% of the market. The gross profit margin of Samsung is 75%. They could put the CapEx in easily to give, but growth is going to be gigabyte growth is 20% a year, and don't expect DRAM prices to come down significantly over the next couple of years. NAND is a different story though. NAND is a different story. You have 5 or 6 companies, and basically they're fighting for market share. So NAND gigabit prices average today 20 cents. A year ago, 40 cents. A year from now, maybe about 16 cents. And we've actually done some cost analysis. So NAND will keep on coming down. But again, you see, now we didn't show it in here, we also have exabyte growth for hard disk drives. So again, what you have here is this dramatic growth in terms of the capacity and also the CapEx. And again, as I mentioned, China is starting. And with 1.3 or 1.4 billion people versus the US having 300 million, you can see capacity goes up significantly. By the way, in terms of some of the digital transactions, Alipay, WeChat Pay, and so on, China is becoming significantly ahead of us. But as the 5G data centers, 5G base station goes in, you're going to see dramatic growth in terms of the CapEx. So it's a good time to be in the electronics industry. It's a really good time to be in the industry. And competition obviously is very strong. As I said, we do see a slowing right now in Q4. We think basically it'll be a slowing Q1. We think Q2 actually will strengthen a little bit. And then in 2020, we do expect a reasonable turn down for non-memory devices. Memory, we think, will continue to be positive. And the key reason is basically slowing of global GDP growth. And then the other one is also we do right now we see some excess capacity in some of the technologies. So again, I think we've covered most of these points, but again, as I said, there are many areas of growth opportunities, and the underlying capabilities that will drive this is adoption and use of AI. So from an EDA point of view, what do we see? Because I think that's supposed to be on the topics today. Again, I think the performance of Synopsys, Cadence, Mentor, Ansys within their areas of focus actually is good. But design costs are going up significantly. And as I mentioned earlier, 75% of design costs are costs of engineers. So the remaining cost is basically the licensing of the tools and then also the computer overhead. So when you look at many of the design costs, especially those that involve many engineers, they don't need engineers. But the first step, of course, to make the engineers more efficient. And so we do see the need for a significant increase in computer power and also new methods of design capabilities and, of course, high levels of abstraction. So the EDA vendors, even though they've done a great job, they make money by the number of licenses they have, the number of seats. So there's no great motivation to reduce the number of licenses. So I think we need to see some kind of disruptive force to have significant acceleration in terms of the enhancements of EDA capabilities and basically how EDA licenses are managed. The first step is to actually put everything in the cloud. And then it's like basically water, electricity, you pay by use. But again, the key issue for them is, how do you do that without destroying the revenue base that you have today? So I don't have a good answer for that, but I can tell you though it's going to happen. I think both Cadence, Synopsys, and certainly I think Ansys are looking closely at this. By the way, the kind of key thing with Ansys, which we are very impressed with, is the use of the tools outside of semiconductor industry. And then basically the approach to the virtual twin, or basically not virtual twin, the digital twin, and then the ability to support the factory automation with digital twin. What we have though is also what we call the virtual twin, which comes back to the smartphone, where you have this capability in your pocket that basically has also not only the ability to figure things out faster, but also basically store huge amount of information. So actually that's a way for effectively a person's life to be extended by having all their thoughts and their data in this virtual twin. Of course, depends on how long the storage of the NAND lasts. So AI is at the kind of starting phase of adoption. As I said, the key driver, one of the key drivers right now is the image enhancement in smartphones. But this is 0.11%. But what you have in your smartphone today is picture-taking capabilities close to DSLR. So this is an amazing achievement as part of the application processor. And of course, the size of the camera module. And of course, the next phase of that, as I said, will be augmented reality and then virtual reality beyond that. But again, the key foundations are processors, but then when you have processors, you have your connectivity. We do think that photonics will eventually come in. We have seen, by the way, a very interesting company in Palo Alto that is doing photonics for quantum computing. And it's basically looks really, really interesting. But again, it's another potentially 5 years away. And then data generation increases the amount of, or the activity in our AI, which in turn increases the amount of data. So it's like a snowball rolling down a hill. Basically, it's going to gain momentum. And again, as I mentioned, it's 15 years. So basically, the people in this room will be affected, and also your children will be significantly affected. So again, as I said, machines will become faster, will be smarter than humans for 98% of tasks. We don't think that IQ in machines has to match IQ in people. But basically, a robot will do a specific task, and will do a specific task more effective than a human can do it. So you basically utilize the capabilities of machines where machines are effective. So, so that's the next phase I think we'll see, or the phase we'll see the next 5 to 10 years. So again, we're basically very positive in terms of the opportunities, and it's a great time to be in the electronics industry. And again, in terms of semiconductors, whether they are hardware, software, and of course the ability to then move up the value chain in terms of providing the full stack solutions. So that's my presentations. If you have any questions, I'll be happy to cover them.
I'm sure there's a few questions out there for Handel. Anyone?
I don't know whether this question is relevant here or not. You shared the cost for 7 nanometer, that is $3 per billion. Do you have the cost for 10 nanometer and 16 nanometer?
Yeah. So the cost for 10 is about 4.5, and the cost for 16 is about 6, something like that. Yeah, I can give you the exact numbers, because what we did was we looked at the wafer price, and we looked at the chip size, and we did a yield analysis, because we have a pretty good idea of the yield. And the 5 we don't have, because we don't really have a good feel yet for UV.
Thank you.
You mentioned time of flight as being a key enabling technology for, is it VR?
No, AR.
For AR, can you mention which time of flight technology are you referring to, please?
Well, basically, we in terms of 3D facial recognition, basically that's mainly structured light right now. But in terms of time of flight, the leader probably today is ST. What Sony has is also looking pretty good. AMS has some pretty good capabilities. A key part of it, of course, is VCSELs. And if you look at VCSEL consumption, because of the Apple slowdown, momentum impact, we have a slowdown. But in 2027, you're going to have a lot of VCSELs.
What I meant was, is it UWB or is it Wi-Fi? It's a radar technology?
No, it's
or?
basically I think it's 930 or 950 nanometers. So it's the laser. Yeah.
Thank you.
Should I?
Go ahead.
Oh, okay. Hey, thanks for the excellent information, and I really liked it that how you encouraged the whole crowd here. This is the perfect time to be in the electronics industry. So we all feel, more valued, I suppose. So coming to my question, let's say I have a business problem where we need to improve the yield for, say, during post-silicon debug. Then how can one get started to apply any of these in baby steps or full-blown, whichever way, to, say, just improve semiconductor yield at engineering level or during post-silicon debug?
Well, we basically had a long discussion with Qualcomm last week, how they're doing it. And it's not trivial. I mean, because it starts with the design. So you have to have enough guard band in the design, and you have to basically also look at the OPC requirements, lithography, and then you have to look at the variations in the process. So for example, getting high yield at 22 is quite difficult because it's a very tight process. 28, you can get very good yields. If you look at 16 FinFETs, basically 16 I don't remember basically it's a pretty good yield. You go to 12, it gets much more difficult. So the design part is a key impact on the yield. So defect densities come down significantly. So then what we look at in the fab are basically systemic yields and parametric yields. And of course, they're depending on how close you are to the process limits. So you have to work with TSMC, or if you're working with Samsung, whoever you're working with, in terms of understanding the distribution of their process and how close you are to the edge. So if you're going to be in the middle, of course, you can get high yields. So it's not a trivial activity. So again, if you're willing to sacrifice performance, if you're willing to sacrifice power consumption, then you can get high yield. So you have to do a trade-off. So what happens in many of these companies, they do the first chip, and of course they want it to work. And then once they get it to work, then they can do some fine-tuning, and they work with a foundry vendor in terms of which machine. But it's really very, very extensive now at 7, because every penny counts. And so it's before, I've run wafer fab, so I've been involved with yields and so on, and today it's a different world. So it's becoming more and more data centric. Now, PDF Solutions, by the way, I don't know how well you know them, they're working with a number of companies in terms of improving yield. So I can introduce you to John Kibarian, the CEO. We have no relationship with him, but if I can introduce you to him, depending on what kind of problem you have and who you're working with.
There's a very nice paper on using ML for DFM on Iowa State University. So I have the paper. I'll be happy to share it here.
Another question down here.
Hi, thanks so much for this nice talk. The question I had was, you mentioned that you thought the EDA would all go to the cloud, and I've heard varying opinions that some people are saying designs won't be in the cloud because of security, IP security reasons, and some people are saying for sure it's going to go. And so what do you think? And also what percentage of designs are in the cloud now, and what is needed to make sure that happens?
Well, we're pretty sure it's going to happen. The issue is going to be when. I think security, I mean, your money is in the cloud already. So I think your money actually needs more security than IP, or at least my money was. But I think the key thing is going to be bandwidth. You know, how you define cloud. And again, you know, will Cadence have a cloud? Will Synopsys have a cloud? Will Mentor, will Ansys have a cloud? Will it be an enterprise cloud? Will it be the Amazon cloud and so on? So we are seeing already the beginning of design activities in the cloud, but it doesn't make sense from a user point of view for everybody to license, you know, this tool, that tool, et cetera, et cetera. But that's how they monetize the business today. So they're going to have to come up with a different monetization method. Now we're working with a couple of the companies in terms of what they're looking at. I can't tell you because it's not public information, but in the cloud you can have, in effect, supercomputer capabilities, and you can actually network computers. So it's going to be a much more efficient way of doing designs. So I think maybe 5 years is a reasonable time window. And I think in the 5 years, maybe you're talking maybe 20–30%. So it's not something that's going to happen overnight.
And I'll chime in on that one. What we're seeing from NetApp's side of the world, that we've got a number of our customers are doing designs in the cloud. If you went to the Design Automation Conference this year, they said it's the year of the cloud. By and large, I think what we're seeing is cost of the cloud is the prevailing factor for not yet moving full workloads into the cloud. Licensing hasn't been an issue because the typical FlexLM licensing works just fine in the cloud in that model. It's mostly that when you're 100% using your high-performance compute environment and your intense high-performance computing storage environments, that's some of the most expensive resources in the cloud. Once the economics start to change, but I don't think security so much is as much a concern. And what we've seen is most companies have started to dabble in all three, AWS, Azure, or Google clouds. So I think you'll probably start to see more.
Yeah, a couple of comments around that. I think cost of being in the cloud should be lower than basically cost of licensing. So I think part of the cost related is preserving the business model, or the resource, or the funding for that transition.
We'll take a couple more questions.
So you hinted on the memory getting closer to the GPU, TPU, whatever, and how it benefits energy and other things. What about computing in the cloud versus computing on your desktop or whatever workstation locally? What's the energy picture there?
Well, again, I think the bandwidth of having everything in the cloud, the bandwidth will not be there. And so for autonomous driving, basically, you can't go to the cloud. I mean, you know, the time issue is critical. But also the amount, the amount of stuff you have on your smartphone, you want to keep it with you. And that becomes also very personal to you. So but in terms of the architectures, we are seeing right now exploration of having small cores with SRAMs. And SRAMs, of course, are expensive, 6 transistors to 8 transistors per SRAM. But then we're seeing now the concept of SRAM planes, and then with wafer-to-wafer bonding. And that's interesting. IBM came out with basically the phase change. We don't think that's going to work because I think the reliability and endurance and so on. But I think but we're also looking at the MRAM structures. Right now, they're not cost effective. But again, I think you have to see a radically different architecture. And again, we're seeing companies that are leaders in the GPU space, or the leader GPU space, working on those things, not announced. But I think in the next 5 years, you'll see a radically different architecture. The other approach goes using a neural network capability, but then the algorithms become very complicated. But you're going to have very high computing power that you carry with you, and you're going to have multiple levels of cloud. You'll have a personal cloud, you have a cloud in your house, and so on. So these things are going to become very common.
We'll take a couple more questions.
Yeah.
We've got one here, and we'll take
I have, thanks for the nice presentation. I have a couple of questions. The first one is, when you're looking at it, you're trying to kind of do a yield analysis and help them improve the yields. How much are you is there any adaptability into going into performance analysis and performance improvement? What's the role of AI in that?
Yeah, that's a very interesting question because as I mentioned, when we look at yield, defect density yield is actually becoming the lowest, defect density is becoming the least important part of yield. So it really becomes the systemic and the parametric yields. And those are tied in to basically how you do the design, what trade-offs you do in design performance, power consumption, and then how closely that's related to the process. So the TCAD space, the back end of design, the physical implementation, that is now becoming a critical part in terms of how you optimize the yields. Also, if you look at performance limitations, interconnect delays is becoming the biggest performance limitation. So the interconnect delays, you can scale the transistor, but then the middle end of line is going cobalt, but after that what you do, and then of course the back end is basically copper. So large grain copper, you improve some, but not much. So how you do the interconnect, how you shorten the interconnect, so that's why things like the fan-out, wafer level fan-out is becoming more important. So it involves a lot of work by the design organization to really understand the process variance and how well you design within those process variants. So the cost, of course, of doing that is increasing dramatically. So again, AI is all data. It's data for the process, it's data for the design, it's data for anything. So what you have to do is you have to manage those data. So blockchain capabilities, frankly, is one area that I think, but again, it's 5 years to 7 years before that becomes mainstream.
Okay. I have second part of the question. If you look at the industry traditionally, they always have some native EDA, which is kind of brute force or something else. But now with AI coming into the picture, how much of the industry is adapting to the new techniques and what you envision and where we stand?
Well, I think today, if you do a design at 5 or a 7, you have to be expert. I mean, you've almost had to do designs in previous technology. So the skill level goes up dramatically. So it's not just pushing buttons. In the old days, you digital designs, you do automated placement around. Today is different. So because of that, the transition or the adoption of AI is really quite complex. So we're actually tracking activities within the EDA vendors and talking to them. But before AI becomes significant in terms of really improving productivity, it's 5 years. So it's not close yet because of the complexity of the databases.
We've got 2 more questions.
Okay.
Yeah, so the question I had was like at some point we had discussion about the GPU capability growing 1000x for NVIDIA processor. So what is the power roadmap for that? Like how is power going up?
Well, it has to go down. It can't go up. But I was going to answer for NVIDIA. But I think new architecture, they're working on new architecture, so I'm confident they will reduce power significantly. Yeah, but I'm not going to answer for NVIDIA.
NVIDIA might tell you that they're actually reducing overall data center power because going from Intel processors to their more dense environments. Joe, did you want to?
Sure, I can tell you my opinion on it. Oh, thanks for that. It's not my first time in a meeting. We like our power-hungry GPUs. We do look at power performance, the ratio between the two. And there's kind of an upper threshold on a per GPU basis, but it seems to be about 300 watts. We can't get much more from most OEM systems. I think there's going to be a market for high power, high performance. And then there's a mid-range market, that's where our T4 fits. That's a 75 watt card. And so there's kind of a low power, enough performance. And we think those are the 2 vectors people are going to go down. There are a set of consumers that are willing to throw power at problems. So the DGX2, that 10 kilowatt thing, we have published a reference architecture that has 9 of them in racks. So 2 racks worth is what our design is. That's 40 kW, sorry, 4 per rack across the racks. 40 kW a rack is what we're telling people for an HPC data center you need to have. So those are the vectors we're looking down. People who have the power budget and will throw power at the compute problem. People who have server constraints and say, within this envelope you can do whatever you can do. And then people who say, I have a significant power constraint, give me the most performance I can get in that factor. And those are the 3 vectors we look down. Very, very tough to get the amount of compute we have for any less power. So it's a strong optimization for us to get there. Because we're at 21 billion transistors in Volta, and that's the biggest chip you can make. It's an 850 millimeter square chip that you can make at TSMC these days. So I don't know how we're going to get any bigger, and we don't get any more power from the OEMs. Does that help? So that's one of the areas we're thinking.
And last question.
Hello. Thank you for a very informative session. Somewhere I got a mixed message that, yes, it is the best time to be in the electronics industry. My question is, where in that industry? I mean, which is the best place inside that industry? And I'll tell you the reason why I'm asking this question, because as the EDA industry is or will move to more and more AI-based or AI smarter solutions, it's definitely going to replace or minimize the design engineers that it would need to use. And similarly, processing capabilities are improving and more AI-based. So where do you see the best place in the best industry that we should be in today?
Sure.
I think NVIDIA might tell you it's a great place to work. and they're hiring.
Yeah, I think there are many areas that I think have good opportunities. I mean, again, we are in NVIDIA, so I have to respect NVIDIA. But I think what Google is doing in some of the areas is really interesting. The medical field in terms of applying AI to medicine is going to be a huge growth area. Autonomous driving cars, the automobile industry is very conservative. So again, we wouldn't recommend that. But in terms of things like the augmented reality, what that's going to do in terms of new applications is going to be huge. The image processing, image analysis. So obviously algorithms is one key area. So again, I think you mentioned NVIDIA has 2/3 in software, 1/3 in hardware. I would actually focus more in terms of the software and then the algorithms, because that's where the creativity is going to come in, and that's where I think you're going to see a whole bunch of new applications. So as we said, we're going to see new industries coming in we don't think about today, the same way that when electricity came in and so on, we have what we have today in terms of social. Yeah. Thank you very much.
Great, thank you.
Okay, thank you.
And we're going to get Santosh Rao wired up. You guys take a little stretch here. Don't breathe too deeply. There's smoke in the air probably still.
But you are already into AI, so it doesn't get any problem. So what's your
That's bigger than we got. That's bigger than yeah, so give me a card. Yeah.
Santosh, you could probably get started.
I think we're going to get started. So if we can request you to take. We're just going to go through it. But I want to thank you again for joining us. I think it's been, you heard from
So we heard from Joe McKinney from NVIDIA on all of the great work that NVIDIA has been doing around the libraries, around the deep learning frameworks and the hardware itself. And we had this great session of all of the possibilities of AI. And so let's take a little bit of time to see what NetApp is seeing in the industry as we work on actual deployments of these solutions. So we work closely with NVIDIA to roll out these solutions to customers across verticals. And we're seeing a broad range of solutions across starter single node GPU systems to some of the largest deployments in the world. So we'll talk a little bit about what does it take to actually go from the technology in the form of components to the possibilities, the use cases, and the 15-year roadmap to how do you get started and what are some of the pitfalls to watch for. So the first thing is you need to be able to feed the system a tremendous amount of data. What we're finding is all of these architectures are multi-petabyte architectures. The more data you feed it, the more likely that your results are going to be well optimized. And you have to look at not just how much of data you're going to feed it, but what is the possibility to keep these GPUs 100% utilized. So to do that, what we've discovered is that the first generation architectures were trying to feed the GPUs in sources of data that existed today. And those systems could not keep up with the GPU utilization rates. So you would see these systems being deployed, but the GPU utilization itself was fairly low. So what has resulted as a consequence of that is we have started to build these turnkey platforms. These turnkey platforms start to bring the data really close to the GPU so that when you look at this extremely high amount of parallelism of the GPUs along with the high performance of the GPUs, getting the data really close to the GPU is the first step in raising the utilization rates for these GPUs. So that's what a platform like this offers, bringing data close to the GPU to raise the utilization rates. So we'll talk a little bit about what these architectures look like. Briefly, the stages of this data pipeline, if you will, are as you see here. You start to look at different use cases for the data ingestion, whether it be the manufacturing lines, whether it be the engineering teams, whether it be the quality teams, or whether it be supply chain and a variety of the, the factory pipeline itself. Data at the edge is being gathered in a variety of different forms. You have digital data, you have time series data, you have log and sensor data, but you're also increasingly seeing that AI takes advantage of image, video, and audio data. So one of the key things in taking advantage of AI is design of your data ingestion endpoints to be able to start looking at what data you're going to collect and how you're going to actually process the data. So part of that is also starting to look at what is the number of endpoints that will collect the data and what is the stages where you have to destage the data. So for example, in automotive, you start to look at how many cars are going to be gathering data, what is the rate of data per car. You start to forecast how much data by quarter and by year based on the number of endpoints that are producing data in the car. You start to look at what is the growth of data per endpoint based on the resolution of data, based on the changing quality of data, and so on. And then you start to build out what is the aggregated data that needs to come out of that edge endpoint and the total number of endpoints that will feed into these systems. The next thing is when you start to feed that into the core data center, you start to look at how many of these data centers need to cross-pollinate data. So data aggregation is also a function of data sharing. Do you need to share data across these data centers, or can you build data centers that will intentionally localize the data, keep the data away from different regions? For example, autonomous driving. So you want to look for, do you really need to train autonomous systems that are being driven in the US on a system that is based out of, let's say, Asia Pacific? So being able to look for optimizations, because these are by definition extremely large data sets. So you're going to look at these data sets growing into exabyte range. In fact, from a NetApp perspective, we are already seeing multiple projects that are exabyte range. The most extreme case that I've heard is a level 5 autonomous that will say, we will produce an exabyte a day. An exabyte a day, right? That is just insane. We as a data storage company are looking at that saying, how are we even going to respond to that? So when you think about that kind of data growth, you have to think about reducing the locality and the footprint of data, and that's where data lakes have to be localized. The other part of what you see is between the data lake and these training systems, which are these NVIDIA GPU high-performance systems, there's a constant flow of data. So not only are you seeing data coming in from these endpoints, but you're seeing data going into the data lake, the data is being cleansed, and then being moved into the training systems. That constant motion of data becomes a challenge at large scale of data sets. So we've actually looked at very high-performance data movers and tried to characterize the performance of these data movers. And we found that today's systems can move about 2 terabytes of data in 25 minutes. So when we start talking about petabyte scale data motion, the current architecture is simply inadequate. So looking at data movement and optimizing data movement is one step, but also avoiding movement is another step. So we'll talk about how NetApp is trying to reduce the motion of data as well. Finally, when you look at training as well as deployment, those are 2 separate but equally important steps. And the key thing to look at here is producing neural networks is only the ingredient. It's like a recipe in the actual cooking process. So you're going to go from a neural network that is trained on about 1/3 of your data set to a neural network that then goes through model validation. And model validation will go through separate mutually exclusive data set testing. So you will take about 1/3 of your data, flow it into the training system, take another 1/3 of your data, flow it into the deployment and model serving system. So you're going to then go through constant testing and constant data flows, where every week or even every few days, as you get new type of data, that data is going to have to flow constantly into these training systems and the validation systems. The validation system might actually be a 2-stage system. First of all, the validation system is a CPU-based system because it is inherently still hosting developer community that is doing model testing and then doing the application integration of those models. But in addition to being a CPU system, it is obviously using GPUs for inference testing, inference validation. So these systems can be 2 different platforms, one being very GPU intensive for the training, and one being a combination of CPU, GPU for a balanced workload that involves developers doing app integration as well as developers doing model testing. Finally, when you look at the role of the cloud, I know there were a number of questions asked about the cloud. We'll go through different deployments that we see across many different customers and verticals. We see the cloud being used for obviously taking advantage of GPUs in the cloud, to take advantage of platforms that are scalable in bursts. So you don't need the full GPU bandwidth and the utilization 24/7, 365 days a year, but maybe you can only use it as and when you need it, turn on and turn off the billing for the GPUs. You can see the cloud being used for the data tiering, because when you have these kinds of exabyte scale data sets, you might want to take advantage of the cheapest tier of data that may be in the cloud. So typically about 90% of the data is cold data, 10% of the data is hot data. So as you look at the training and the inference validation, that is only about 10 to 20% of your total data. The remaining 80%, you want to stage the data out, and there it is a choice of whether you use the cloud or you use on-premises for cold data. So let's look at what this data looks like. One of the things that NetApp has is the ability to get a lot of telemetry out of our systems, including many of your own systems perhaps. ActiveIQ or ASAP gives us very fine-grained statistics on systems in production. So as we look at these systems being deployed out there, we are able to look at what kind of data set, what is the nature of the workload, what is the nature of the namespace, are these broad or shallow namespaces, what is the file sizes, and so on. So firstly, when we start looking at the ingest workloads, these ingest workloads, depending on the type of the device that is producing the data, is producing very small time series data, or is producing image video data that may be really small, images maybe 50K, 100K, 256K, and so on, or it is producing continuous streams of video or even audio. Continuous streams of video, as in, for example, if you look at the modern aircrafts, you're seeing these camera feeds that are continuously coming from the aircraft. And that is an example of digital collection on every flight. You're seeing that data being gathered, that becomes the feed on which you can perform training and start to build AI use cases. So you're looking at a combination of write-heavy use cases, sequential data for video and audio streams, small to large files may be actually for image or time series data. As they come into the core, you're going through the data preparation or data cleansing phase, where you have a combination of compute stacks, such as the Apache stack, being used for cleansing of the data. You're seeing a combination of read and write because you're modifying the workload. So on the one side, you're reading the data coming in from the ingestion points. On the other side, you're cleansing, transforming, and augmenting the data. So what we mean by that? So cleansing involves a few different steps. For example, if you're dealing with images, you need all of the images to be cropped to the same size. If you're dealing with images, they all need to be the same resolution. If you're dealing with images, you cannot mix different types of color backgrounds on the images. You have to look at constant color formats for the images. Similarly, when you look at video and audio feeds, you have to go through the process of augmenting and cropping some of these streams. So all of that generates a balance of read and write heavy workload that is being performed on what is typically a CPU system, but as you heard from NVIDIA, they're starting to participate in accelerating the data prep as well. So the role that GPU plays is to bring the parallelism and acceleration to different stages of these data pipelines. So traditionally, you've seen NVIDIA start to accelerate training and inference. This is where they've started from. Now they're moving up into accelerating transform and explore phases. So next, when you look at explore, once again, this is taking advantage of in-place visualization of the data sets, in-place visualization of the pre-prep and post-prep training phases. And so you're looking once again here at very read-heavy workloads. Most of this is read-heavy, and you're looking once again at random access to some of these workloads. Finally, when you get into training, this is where you're seeing very unusual workload patterns. You're seeing millions of files that may be very, very small in size, 50K, sometimes even 10K in size. So the reality is that neural network data is being produced in ways that is not optimal. So these data sets are not being built out in a structured way that allows you to optimize the data. So you might see 10K files and several tens of millions of these files. And you may see it all in a single directory, or you may see it all in different unoptimized directory formats. So the needs of a training system is that it is able to deal with a mixed workload that is either small file reads or large video and audio stream reads. So you have that mix of, it has to be both sequential and random. And as you heard earlier from Joe, synthetic data, or fake data as he called it, is a new trend in neural networks. So they start to create GANs, or generative adversarial networks, that would produce the data. So when they produce the data, they start doing some writes, and the more you see GANs producing synthetic data, the more the write workload increases. So the key takeaway here is you need to architect for systems that can handle a mix of random and sequential workload, and that can handle a mix of read and write workload, and have the fat pipes to stream data constantly, because these are systems that are just, pipeline is a very symbolic term for it, it's constantly flowing. Just like you have your gas pipelines and water pipelines and electricity lines, these are constant flows of data on a day in, day out basis. There is no way you can turn it off. Once you start these systems and you start employing autonomous systems and AI systems, there is no turning it off. So you have to build for these constant pipelines. So across these pipelines, we offer a number of solutions. We offer small form factor solutions called vector data and PackStar, which are partner-based solutions that are really small, about the size of the notebook that you see, that will allow you to do data ingestion. We have solutions that will allow you to move the data in smart ways, such as SnapMirror, that will reduce the amount of data footprint, that will dedupe the data, both in motion as well as at rest, and that will only move unique blocks. So you look at data movement across source and destination, compare what blocks have been sent, and only send unique blocks. Cloud Sync is a data mover that can move data directly into object formats. So for those of you that are looking at cloud-based deployments, if you want to ingest the data at the edge and take it directly into S3 in the cloud, we have Cloud Sync that can give you that kind of data movement. We're also delivering some of these small form factor Apache Hadoop stacks and Hortonworks data flow stacks that will allow you to take time series data and streaming data using tools like Kafka and NiFi through these small form factor systems. So think about running not just these Hadoop stacks, but running it on small systems that can be the size of that notebook. Finally, in the core, you're going to have hot data, cold data, and the mix there is going to be about 10% to 90%. So we're giving you the choice to run hot data in all-flash system, hot data on a hybrid system where you can mix that 1090 ratio within a single system, like the FAS hybrid. You can have cold data systems on premises that are storage grid, and you can have white box systems that are commodity price points. So you can take that whole range and decide how you architect your 10%, 90% mix of data. Finally, we are also looking at what's called max data, where you can have persistent memory. So when you start thinking about performance for these systems, and when they talk about GPUs will be 1000x the performance in the next several years, we are looking at what it takes to give you 1000x the storage performance. So Flash got you into the 500 microsecond range from a latency perspective. NVMe and NVMe or Fabric brings you into the 200, 300 microsecond from a latency perspective. System like Max Data with the technologies around persistent memory, which is technologies that basically take advantage of writes to your DRAM like architectures, will get you down to 20 microseconds. So we are now looking at systems that will tier the data, starting with a SLA of 20 microsecond, going out to 200, 300 to 500, and then to the backend cold store. So let's look at what these deployment options look like. There are 5 types of deployments that we see, and I'm going to go through these in some level of detail. The left-hand side is the most commonly seen deployment. This is where most customers are at. 90% or more of the customers start with where they're at and say, okay, how can I build from here and take this forward? The second option that you see is a little bit more advanced, but several customers, particularly in the EDA segment that have used NFS in the past, are actually well placed to start in the second spot. Because if you're using a file system that provides you the ability to feed a variety of data sources in that pipeline stages, you can start to share the data format. You can start to share the data across different compute ecosystems and take advantage of it. The third takes a step that is radical and says, okay, if my data is exabyte scale, I want to start at the lowest price point. All data will be in the coldest tier, and we will promote based on policy, like I want the last 2 days of data for training, or I want the last 1 week of data for training. So the third step basically says, start cold and promote only as needed. So the analogy of that is, if you look at, about 10 years ago, bare metal servers were the default. High performance with bare metal. And somewhere in that 10-year stage, you started seeing exception tickets to say, justify why you want bare metal, otherwise the default is virtualization. So you'll start to see the same kind of shift towards, give me the coldest tier and then promote into hot data as needed. The next two are cloud and near cloud options. And as you take advantage of cloud, there are multiple reasons to use the cloud. One is for the IP. The second is for the bursty nature of the compute. The third is for the cost. You don't have to build out the CapEx on premises. You can take advantage of the CapEx in the cloud. But the flip of that is, if you move data into the cloud, it can be very challenging to get that amount of petabyte scale data into the cloud. And these AI systems are closed loop systems. So you're going to have AI inference being pushed back to the edge devices, like your cell phones or those sensors in the cars. You're going to have the neural networks being pushed on a daily basis, hopefully over time, and so on. So when you count the number of endpoints and you aggregate the amount of data across those endpoints that needs to be pushed out and the frequency of those rollouts, your cloud egress costs go up. So you have to anticipate what is your cloud egress cost and forecast that over time, and then be careful to use the cloud only for compute but not for data. So if you do that, that then takes you to the near cloud option. So the near cloud option then says, I get all the benefits of compute, but I don't pay the cost of cloud egress. I don't pay the cost of bulk data movement into the cloud. I can separate compute and data and then achieve the best of both worlds. So this is where 90% of customers might be at today. You have a variety of file systems. Many of you use NFS today. You may have some parallel file systems. If you're doing HPC, if you're doing Lustre or GPFS-based deployments, you may have those as existing data lakes. If you're using Hadoop and big data lakes, those are typically HDFS. They may also be NFS. And if you have time series data, sensor data, log data, and so on, you have either Splunk or Elk, and you have NoSQL databases. All of these turn into feeds into these GPU farms. So what happens is you start out with these systems as it is. You simply procure and deploy a GPU server, and you say, okay, I'm going to move the data. That's the first step everybody takes. The problem with that, like we started out, is you can't keep the GPUs utilized. So the question then comes back, okay, I spent $1 million on this GPU CapEx, and it's just sitting idle. What am I doing with this thing? Justify why I have it. And I'm not taking any advantage of it. My data scientists aren't doing anything, so I don't even need a data science team. So the whole process goes backward. So then you need to start thinking about, how do I get these GPUs utilized? Part of getting the GPU utilized is feeding data into these systems at a rate that keeps them constantly utilized. That requires parallel streams, because you're pulling, remember, you're pulling random samples of 10K, 50K, 100K images. So when you look at these systems, the GPU farm might be close to where the data science team is. For example, Silicon Valley. You may have all your data scientists in Silicon Valley, whereas these back-end data sources may be in data centers in the Midwest for power reasons or cooling reasons and so on. So you have data that is flowing across WAN bandwidth and at small footprint of 5K, 10K, 50K, random samples. So you have a compound mix of problems, and you cannot aggregate that because you intentionally need to do random sampling of data. So when you look at neural network training, the goal of training a neural network is to intentionally feed it randomized samples of data so that the model is robust enough to deal with the variety of conditions. So as you look at autonomous driving again, you want to feed it samples of data that may be midnight, early morning, late night, smoky conditions, foggy conditions, dust storm, and so on. So you're constantly doing random reads, and that requires a certain amount of traffic optimization, which you cannot do. You're inherently going to be unoptimized in these deployments. So the next step you take then is you put a file system close to the GPU, and you set up these algorithms to do staging of data. So you have staging from the data source into the local file system. You have staging from the local file system into CPU pipelines. Then you have staging from CPU pipeline into GPU pipelines. So you have that constant flow of data. Finally, the next step you can do is a solution like Max Data, where you have persistent memory that sits right by the CPU. So we have gone from taking data sources that are remote to data sources close to the GPU to now data in persistent memory close to the CPU, so that you're able to then feed the CPU pipelines. So this is the first step which you can take, which is optimize what you can. The next step you can take is to basically look at being completely in place. So what we mean by in place is many of your deployments might be NFS already. If these are NFS systems, and these are high-performance NFS systems, such as AFF A800, for example, they have enough of horsepower, and we'll show you some benchmarking we've done, to be able to feed both the GPU system and the CPU system. So you start taking a high-performance A800, having your data sources hosted on clusters of the A800, now you have the ability to not have duplicate tiers of data that need data movement, but the data source is able to feed into the GPU system, particularly when you combine it with a solution like Max Data or FlexCache for that matter. So solutions that give you caching close to the CPU, combined with high-performance solutions that are hosting the data source, will avoid the data movement. So all that motion comes to a halt. You don't need that motion if you don't have discrete systems. So that's the next step. Many of you may be in a position to do that. The other trend that we should talk about is customers want to hedge their bets. They want to look at, hey, if cloud gives me faster path to innovation, I need to have one leg there. And secondly, across the clouds, if GCP tomorrow overtakes AWS, I want to have a leg in both places. So one of the innovative trends we see is a tri-cloud architecture. A tri-cloud architecture says, my data is going to be where it is today. I have a backup copy in one cloud. I might have a second backup copy, two copies, in another cloud. So that way I have 3 copies of the data. I need a backup copy anyway, but now can I use the backup for my AI? So with technologies that we have, such as SnapMirror, and now the more recent NDAS, you can actually expose a native object format of the data so that you can apply a cloud AI stack on what is your backup copy. So you need that backup copy anyway, but you start taking advantage of, can I apply a GCP stack in addition to my own stack and look at what are my benefits there. The third option we talked about is cold data, and then moving cold data into the hot system. So storage grid web scale gives you the ability to get down to cents per gig. So when you're talking exabytes of data, you really want to get to the cheapest, absolute cheapest tier, and you can start with storage grid and then apply policy-based movement where you say 2 days, 3 days, or 5 days of data goes into these systems. The challenge to watch for is, even though you may in training feed the last 2 or 3 days, you need to retrain data periodically on a wider sample. So you may have to go back every month and retrain on the last month of data. So that requires a sweep that may be too slow for a system that is cold data. So that's where you have to make the trade-off between, do I go with storage grid, or do I go with FAS, or do I go with commodity-based on-tap select? Those are some options, because you're not just performing for the last 2 days of data, but you have to keep in mind every month you may have to sweep across that multi-petabyte data set again. So those are some things to keep in mind. As you look at the cloud, this is a very easy starting point. You could start out within 30 minutes. You take advantage of cloud volumes. You get some credits maybe for cloud volumes, and you deploy a cloud AI stack or something like SageMaker on cloud volume. You get started right away. So many times, this is the fastest start. You prove out that this has a value, especially if you've never deployed AI before. You don't need to start by buying hardware. You just start in the cloud, prove the concept, show the concept, then you turn into actual CapEx. And then finally, NPS as an external solution. So we looked at a variety of different deployment models. Now we look at different data moves. How do you actually move the data across these different systems? The data is in the data lake. You need to move it into AI system, and you need to constantly sync depending on the data source. As we said, if the data is Hadoop, you may have HDFS. You need to sync between HDFS and NFS. Similarly, you may need to sync between GPFS, Lustre, NoSQL, Splunk, Elk, and so on. So here's a couple of examples that we'll show. In this case, you're running your data processing for data prep and cleansing on the Apache stack on Hadoop. And basically, this Hadoop system is going to feed data into a second copy on NFS that is then feeding into the ONTAP AI GPU system. So you have the same data basically being transformed into a copy that's on NFS that is feeding into the GPU system. Now, the next thing that we want to see is if you're doing this in the cloud, let's take an example here in the cloud. So this is an on-prem deployment in the cloud. They're using a combination of HDFS and NFS. They're using HDFS for the management stack. They're using NFS for in-place data. This is what we call the NetApp in-place analytics module. So now you're creating a clone of the data set, because this data set is already in the data lake. You have labeled the data. You have cloned the labeled data. And you can expose the labeled data through NPS, near cloud, to multiple cloud stacks. So you're now taking advantage of 4 analytics stacks alongside with an AI stack. You have an on-prem analytics stack. You have the cloud stacks. But you have only one physical copy of the data, at least as far as the on-prem is concerned. The clone is pretty much a logical sharing of the data. SnapMirror will once again set a baseline and then have logical differential blocks of the data. So what we are showing here is some of the most advanced customers doing what are called tri-cloud or multi-cloud architecture, where they run analytics plus AI on a shared data set that is cloned for physical isolation, and they have a copy in the cloud to hedge their bets. So now you're completely insulated and future-proofed. The next thing that we talk about here is, I'm just going to skip ahead a little bit. The next thing we talk about is going across object formats. So when you're dealing with on-premises data, you're dealing with traditional file. But many times, if you want to deal with AI in the form of SAS and PAS, you need the native cloud format of data. You can't use NFS. So in those cases, you want to convert from object to NFS, or you want to convert the other way as well. So for example, let's say your cloud egress was a consideration. You want to put ONTAP AI outside the cloud in Equinix, but you have data lakes that are in the cloud for all of your microservices applications. So now you need to move from object into NFS. So you have use cases that need NFS to object and object to NFS. And we provide you a data mover that allows you to track these relationships, to track state, and to resume these relationships if you have any kind of breakage of the relationship. And you can have data movement bidirectionally from NFS to S3 or S3 to NFS. So the takeaways here are you are going to need to extract data from different data sources. That data is going to need to be constantly moved at high performance. And that maximum performance can be achieved certainly by adding more bandwidth, by doing link aggregation, by doing multiple levels of network links, and so on. You can schedule it and have on-demand data movers that can be tracked. You can have efficiency of movement by using technologies like SnapMirror that reduce the number of blocks moved. Or you can have zero cost for data movement because you're using in-place shared data across both analytics and AI. So many different takeaways depending on brute force, optimized, or smart. So those are the choices you have. Finally, as you look at edge data systems, this is where AI starts. It's these edge use cases that start to produce all that sensor data, all that camera data, all the video and audio streams. You need to be able to not only gather this data, but you need to think of smart ways of aggregating this data and moving it in. And that's where we start to partner with a variety of hardware vendors. So our ONTAP solution runs on white box, obviously, that's ONTAP Select. We have taken it a step further where you can run it on partner platforms that come in semi-rugged, non-rugged, or rugged form factor and give you aggregation of data on a daily requirement. So you can put one of these systems in the back of those path planning cars. You can destage data from the path planning car. You can put one of these systems by a drone, an oil rig. These systems actually today get deployed in police cars. They get deployed in the military front lines. So many different ways that data can be collected and destaged from a data movement perspective. So the platform, as you looked at it, these platforms are basically 3.5 kilowatts each. Each DGX is 3.5 kilowatts. We are showing a sample architecture here, but the architecture can scale from single node, which is 3.5 kilowatt, to 100 node, which you can do the math, significant amount of power spread across racks. So some of us, in fact, just came from looking at one of these as a 10-node deployment today. As Joe was saying, we have a 10-node deployment across 3 racks that we are testing with right now. So this is the architecture. It runs across the DGX from NVIDIA, the all-flash system from NetApp, and uses 100 gig Ethernet switching for that data movement, and takes advantage of the NVIDIA GPU cloud, which is a containerized stack for all of the applications, and takes advantage of many of the Trident container orchestrations as well. So you can start really small in your existing racks, no power changes needed, no rack changes needed. You may scale that into 2, 3, 4, 5 type clusters. Or you may decide this is infrastructure that is for the future, so I'm going to build new racks that are state of the art at 35 kilowatt or 47 kilowatt and start to rack up these systems for the future. You can also in IT start to consolidate line of business where you have a 10-node system that can host all your lines of business. So instead of building for each line of business, you can start to consolidate in the IT systems and start to build these out. And you can scale them non-disruptively starting at the really low end. This is where most customers will start for a starter solution. But if you know that line of business has proven the concept and you're going to scale it and your scaling is your competitive advantage, then you can start where you want to be. If you know you're going to be at the high end of this spectrum, you might as well start there, future-proof yourself, and scale out from there. Or if you want to just prove the concept out, you take a single DGX with a single 220 and build that solution out. So we give you the full range, and it's a pretty non-disruptive scale out. So in terms of performance, so within my team, again, from an engineering perspective, we have these systems in-house. So I have 4 of the DGX systems in our team, plus we have a DGX2 that's coming in, and we have the DGX workstations, and we also do these tests in the cloud. So we produce a number of these benchmarks that are available for you if you would like to see it. All are on netapp.com/AI. So if you go to netapp.com/AI, we have the reports that give you a full range of the performance by neural network. So you'll see on the right-hand side, we are showing each neural network, what kind of performance it needs, what is the CPU utilization and the bandwidth, and we have reports that go into images per second for training and inference for these neural networks. The takeaway is each of these systems, when combined into, let's say, a 4-node cluster, is about 5 gigabytes of bandwidth. 5 gigabytes of bandwidth at about 20% CPU utilization. So these systems have the headroom for you to consolidate analytics and AI. They have the headroom for you to build scale-out GPU clusters, or they have the flexibility for you to start low with A300 and then scale up as you need to. So those are the choices you have as you look at this range of solutions. We make sure that your data movement is automatic for cold data. So when we said 80-90% is cold data, that separation of hot data from cold data is done automatically without needing any policy. You can apply policy engines as well, but if you choose not to do that, we will handle hot versus cold automatically for you. So the key takeaways that we talked about today, it's a validated architecture. It speeds you up to all of the different degrees, raw brute force methods, smart methods, or data movement avoidance methods. These are engineered to give you the scale that you need across these workloads. And so all of the different things that we covered, you get extreme capacities, extreme performance, edge solution, a cloud solution, automatic tiering to the cold data tier, and the ability to look at some other things such as compliance and data protection. Those are some of the things that you get to look at. So with that, we have a number of resources available that will be shared as a part of the slides. Many of these resources are easily found off of netapp.com/AI. We have several customer blogs. So one of our advanced customers who has been doing deep learning since 2012 does a blog for NetApp series, so that is available as well, and several podcasts and webcasts and so on. So happy to take any questions at this stage. All of the papers are available off of netapp.com/AI, easy website. So if there are any questions, we're happy to take any last questions here. Otherwise, we want to thank you. It's been a great session. We want to appreciate all of our speakers here and a fantastic session. And I think, MJ, if you want to do some wrap up, feel free to.
Yeah, thank you, Santosh. Thank you, Handel. We're looking for Joe. You're welcome to come join us upstairs. It looks like Joe might be coming in right now. We're going to head upstairs. They actually have a nice bar up on the top floor of the new NVIDIA building, and we'd love you to come and join us for some appetizers and cocktails, and Joe will escort us upstairs. If you need to leave, we understand, and we'll also escort you out to the lobby. So if there's no more questions, let's go mingle, and there's Joe. Ready to go? Okay, thank you.